So what is the minimum time?
Okay. I'll actually sort of start with the proceedings as people join in because I have a kind of a long introduction. First of all, we welcome all of you back to the NSF colloquium on a Wednesday. It's been a little bit of a hiatus for us since it's slightly on the edge of the vacation period and people often go off for other kinds of things from the institute. So these colloquia is pretty rare, but we had to do it because my colleague Bahadur Singh, who actually is from the Department of Condensed Matter Physics, he actually recommended that we have in works of a possibility of Professor Tanusri Saha-Dasgupta coming over and on a Wednesday pretty much end of this month. And I thank him for organizing this trip, Bahadur. I also thank many of you for joining in to the lunch today. And of course, I hope more faculty members and students will join in the colloquium. So an introduction I have to give because it's important that we sort of first introduce the NSF colloquium again for everyone. This is an idea that originated from Professor Homi Bhabha, who was the founding director. And the idea was to bring all the natural sciences faculty members together for one session of a colloquia where people coming from outside TIFR would visit, and Bhava would also visit on a Wednesday because he was busy with other activities in BARC, and allow for a discussion on one topic in any important field in natural sciences. So this has been a tradition for ever since TIFR existed. So I really welcome Professor Tanusri Saha-Dasgupta for coming through this particular academic channel because it's highly deserving. And I just wanted to sort of introduce that Professor Saha-Dasgupta works in the area of computational condensed matter and materials physics. And a major thrust of her research is the application of first principles electronic structure calculations to understand the physics and chemistry of novel and complex materials. She obtained her PhD degree from Calcutta University in 1995, and she was a postdoctoral fellow at the Onera Paris CNRS, and then Max Planck Institute Stuttgart and ISC Bangalore. Saha-Dasgupta joined SN Bose National Center as a lecturer in 2000. She is currently a senior professor now, as well as the director of the institute. She has been a fellow of the American Physical Society, the World Academy of Sciences, Indian National Academy of Sciences, Indian Academy of Sciences, National Academy of Sciences India, and the West Bengal Academy of Sciences. She is a recipient of the Swarna Jayanti Fellowship, the MRSI ICSC Superconductivity and Material Science Annual Prize, DA Raja Ramanna Prize, and also Dr. APJ Abdul Kalam HPC Award, along with the JC Bose Fellowship. She has been, of course, one of the most important members of the condensed matter physics group in the country. And it's actually a privilege and pleasure to invite you here for this colloquium. Tanusri.
Thank you so much for the kind introduction. And let me start by thanking both Bahadur and Jyotishman for having me here. It's nice to be back to the TIFR campus after a break of quite a number of years. And I enjoyed my day in the sense that it has been packed with so many interaction and so many engrossing discussion. And sometimes I had to cut the discussion because of the just lack of time. So I do hope this is a good beginning and we will continue this interaction. And in fact, the invitation letter that I received from Jyotishman said something to talk about magnetism and topological superconductivity, very specific. So those who have come here to expect such objects, you won't find, because I will really not talk about magnetism. I'll talk about some bit of superconductivity, but certainly not topological superconductivity. So as has been already mentioned, I come from SN Bose National Center for Basic Sciences in Kolkata. And this institute came into picture in the year 1986 and was set up by Department of Science and Technology to basically honor the life and work of SN Bose. Those who are physicists in this room would know his name because half of the fundamental particles of this world, namely the bosons, are known by his name. So as the title says, it's actually a tale of two stories. So I'm going to tell you two stories. The first story is about some metal insulator transition, and I will explain what I mean by that in some specific peroxide, and we will show actually a class of peroxide we think will belong to this family. It is just not this particular one. So let me start with peroxide. I think it's a colloquium, so I will start in a colloquium spirit. So those who are condensed matter physicists, they at least know the name peroxide. Those who are not condensed matter physicists, by the proximity effect, by this time you also know what is a peroxide. So the peroxide are the compounds which are of general formula AbO3, where generally A is an alkali, alkaline, or rare earth cation, and B is generally transition metal, and O is, of course, oxygen, and that's the kind of the crystal structure of a cubic AbO3 peroxide. And the whole idea is the physics or the chemistry is set by the transition metal d electrons and the oxygen p electrons, where this A cation gives just some cohesion in the structure. So in other way, you can treat them as some observer or a spectator. And it is decided by the entire science is decided by the two energy scale in a simplified picture. And these two energy scales are U and delta, U being the energy that is required to move one d electron from one transition metal site to another transition metal site, while the delta, which is known as a charge transfer energy, and U is basically known as a Hubbard U, that's basically Coulombic in nature. All of them are Coulombic in nature. This delta is the energy that required is to move a p electron from oxygen to the transition metal site. And the entire thing actually is given by a phase diagram, which is known as Zanin-Swatsky-Allen phase diagram, that if you are at the early transition metal, early in the periodic table, among these two energy scale, the U is less than delta. As a result, a metal to insulator transition happens by switching on this important interaction parameter U, where the gap opens within the manifold of the transition metal D in terms of having a subband, which is known as lower Hubbard subband, and which is filled if you are a half-filled state, and an upper Hubbard subband. And therefore, a metal to insulator transition happens just by turning on this correlation. A different picture shows up if you are the late transition metal. See, in this case, the transition metal was titanium. In this case, it's a late transition metal copper. And in this case, actually, by turning on the interaction, because U is much larger than the delta, the gap opening happens between the filled oxygen p bands and the empty upper Hubbard band. And the gap is a charge gap rather than a Mott gap. And this can lead to a negative charge transfer situation in the sense if the bandwidth of this oxygen p band and the bandwidth of this upper Hubbard band, which is empty, gets overlapped, meaning the width of these two bands, small w and big W divided by 2 is greater than delta, what you get is a metal and a partially filled oxygen band. That is known as a negative charge transfer situation. Pratap, any question?
Yeah, so I'm thinking that two is whether the oxygen orbital matters.
Absolutely. Absolutely. Because if you think of some excitations, they will be different. A concrete example of that are the Cupids superconductor. In this case, the copper is 2+ and D9, and therefore you have one hole at the copper side. Now, if we dope this material by which you get the superconductivity, we introduce additional hole by hole doping. But this hole, instead of going to the copper, it actually goes to the oxygen and therefore makes a singlet pair. So the hole at the copper side and the whole doped hole that goes to the oxygen. And that gives rise to a very famous concept like the Zhang-Rice singlet. And the evidence of such thing is actually a spectroscopic signature. If you do an oxygen KH spectroscopy, Kalu is not here, he is an expert on it. you see actually a pre-peak, and this pre-peak grows as you are doping more and more, saying actually the holes you are putting in the system, instead of going to copper, is going to oxygen. And is it the case only for the cuprates? Now there are growing evidence it is just not cuprate. It's even in the Nicolette. For example, this example, nickel oxide, you replace some of the nickel by lithium. That means nickel 2+ divalent, you replace with lithium, which is monovalent. So you are therefore putting some holes, but the holes are, instead of going to nickel, they are actually going to the oxygen 2p, which is again proved by the same oxygen KH spectroscopy.
Can I ask a question?
Yes.
So, the idea here is that you're doping that oxygen instead of the copper, where you were doping these systems. Is there also a bond length change that is observed in the copper oxygen distance?
Yeah, so I will actually come to it because my entire talk is based on it.
Okay.
The nickel oxide structure is basically just a rock salt structure. So then it comes to the same nickel, because I will be talking about nickel, the rear earth Nicolette. That's again some topic which has kept the people busy for quite some time. And those who work with peroxide, they know a famous structural concept is the tolerance factor. Tolerance factor is nothing but a geometrical factor, which is defined in terms of the ionic radius of A cation, B cation, and X, which actually means oxygen. And depending on the tolerance factor, because by changing this rear earth, you are basically changing the cation size at the rear earth side. And this is the kind of tolerance factor versus temperature phase diagram. And what you actually get below a certain temperature for most of them, except lanthanum, actually metal to insulator transition happens, and sometimes together with a magnetic transition. And these transition, people so far have thought about what is known as a charge disproportionation transition. Rear earth is 3+. I will have quite a bit of chemistry, so I hope which will be fine. So rear earth is 3+. So if you just do a charge balancing, nickel will be 3+. Nickel 3+ is D8. And nickel doesn't like to be really D7. So it likes to be D8. So the whole idea was you take 2 of the D7 ion, and that charge disproportionates into one D8, another D6. But that's really not the case. Nickel remains D8. It doesn't go anywhere. Rather, you have a ligand hole, that means a hole at the oxygen side. So what you call as D7 is actually D8 with a ligand hole. And you have 2 such objects. And what you form, that one of the nickel acquires 2 of the ligand hole and forms this S = 0 object, and another one remains devoid of the ligand hole. You just asked about the bond length. Indeed, that gives rise to a bond contraction expansion, like a breathing distortion in the entire lattice, which is also actually a signature of a charge density wave. So it's a charge density wave, but that charge density wave is in terms of the ligand, not in terms of nickel electron doesn't do anything. That's the point. And there are a few papers from the experts in this field, like Swatsky, Millis, and etc. And there are actually experimental signature of it. Now, as I said, if you increase this tolerance factor, actually there is no metal insulator transition. For example, in case of lanthanum, all the way it remains a metal. Now, what happens if I replace lanthanum 3+ by bismuth 3+?
Just a quick question and then we can move on.
Yeah.
Is it possible to see a super exchange between these sites?
Yes.
Where the electron and
for example,
or the whole.
So this is I don't want to get into details because this is not my work. So here also it's a site selective Mott insulator because the Mott transition happens only in this site being already an insulating object, and this site is completely non-magnetic object. Only this nickel becomes magnetic. So what happens if you replace lanthanum 3+ by bismuth 3+, which is larger in size? You would expect it will be even a better metal, but there is a twist in the story. It's actually an insulator. So that's a question, what makes it an insulator? Then the other surprise, I think all the solid state chemists, they are great genius, and in our country, I would really recommend to have more solid state chemists if you want to strengthen your condensed matter research. I completely believe that, whether you like it or not. So these great solid state chemists. What they did, they took this insulator and put pressure, and then they could drive an insulator to metal transition at a critical pressure of 3.5 gigapascal and with a volume collapse. Volume collapse is 2.5%. And then what they do is, what the chemists do quite a lot is called bond valence sum. And by this bond valence sum, they find actually the bismuth at the ambient condition. There are two different sites of the bismuth, bismuth 1 and bismuth 2. And what they proposed a picture, which I will show you a little later. And this got some attention because they found such kind of this insulator to metal transition can be also driven by temperature. And you would expect by putting temperature, your system will expand, but here it collapses. So it's a negative thermal expansion. And they got some patent and etc. out of it. So this is their proposed mechanism. They said that the bismuth is not in a 3+ state. That's wrong. Bismuth is in 4+, nickel 2+, and O3. That's the situation. And since bismuth doesn't like 4+, bismuth charge disproportionates to 3+ and 5+. And by putting pressure, what I'm doing is a charge transfer between bismuth and nickel. So instead of bismuth 4+, nickel 2+, it becomes bismuth 3+ and nickel 3+. And with this rare earth Nicolette knowledge, then this 3+ should also charge disproportionate, which they don't see at all. So there are several questions. Is it too simplistic view? Bismuth 3+ will be 6s2. Again, you need to know a bit of chemistry. Bismuth 5+ will be 6s0. And 6s is quite deep down. So to make it completely empty, you have to actually, from modeling energy perspective, it is probably impossible. And why you don't see this state? And there have been actually some calculation. In our case, we will show actually with the pressure how it happens, but temperature has a similar effect, very similar effect. But in our calculation, there was no temperature. We mainly probed the pressure effect. D7. So there are two calculations. It's a very similar calculation. There was one TRL which did some Hartree-Fock kind of method, and subsequent TRB where they did the DMF, did the dynamical mean field theory. And for the bismuth, actually their model was based on only bismuth and nickel, no oxygen, nothing. And there was a famous, quite some time back, there were this valence keeping ion, because bismuth is a valence keeping ion. It doesn't like to be 4+, and there were concept of a negative U for this valence keeping thing. And long back, it is from Harrison who said that modeling by this negative U is actually not a very comfortable thing, and you instead should bring about the lattice, which you have not really considered at all. So we find that there are two major lacuna. One is the role of the ligand is completely neglected and ignores the crucial role of the lattice. So we did some density functional theory calculation. I will not go at all with the details of it, but this just shows that the density functional theory is capable of capturing this volume collapse and also the change between this ambient pressure to high pressure phase, correctly showing the transition. And even we had a very good agreement with all the structural parameters of the ambient pressure phase and the high pressure phase, saying that the density functional theory is able to capture the essential physics. Now, what we look at the density of state at the ambient pressure phase. Just for those who are not used to see density of state, this has two panels, and each of the panel has up and down spin channel. And projected to bismuth 1 in the ambient pressure phase, I forgot to mention it, in the ambient pressure phase, you have two different bismuths and with two different sizes of the bismuth polyhedra, one large and one small. In the high pressure phase, the bismuth, there is only one kind of bismuth, and you have uniform bismuth oxygen polyhedra. So first of all, what we find that both bismuth 1 and bismuth 2 has this deep 6s state on both bismuth. So that means it is indeed not possible to make the bismuth 6s empty. This bismuth 2 instead has a split of state. The zero of the energy is at the Fermi level, has a split of state, which is shown here. And very interestingly, this split of states has its partners it finds at the oxygen. So that means the oxygen 2 minus, which should have been completely filled, it is not at all filled, rather it has a split of part which has its partner with bismuth 2. And this is seen in the calculated moment because oxygen, which should have been non-magnetic, actually acquires a large moment on the oxygen. So therefore, our conclusion is in this ambient pressure, this compound is not really like bismuth 3 plus and bismuth 5 plus. Rather, it's all of them are bismuth 3 plus. One bismuth has no ligand hole and another bismuth has two of the ligand hole. Very much like the nickel story I was trying to tell you. And the nickel, of course, remains as nickel 2 plus. Now, what happens at the high pressure? At the high pressure, there is only one kind of bismuth. You can see that it has this deep 6s state and no split of state, even if there is a little bit of thing that you can see because of the mixing with the nickel. Instead, the nickel electronic structure changes a lot, and it has these states which has now its counter states with the oxygen. Oxygen again becomes empty, but now it looks more like, resembling more like the nickel instead of the bismuth. Just as a comparison, I flash again the ambient pressure electronic structure. You had this split of state, which looked very much resembling like the split of state of the oxygen. In the high pressure, you do not have anything on bismuth, rather you have nickel, and the whole thing has become metallic. This was insulating, and the empty nickel states looks very much like the oxygen empty state. So therefore, the high pressure electronic state, instead of actually nickel 3 plus it doesn't like to have, is nickel 2 plus with the ligand hole and nothing on bismuth. So what is actually happening, and this is seen in the spectroscopy. So what is actually happening, this is basically a change of covalency. I have a ligand hole. The ligand hole at ambient pressure decided to be very close to bismuth, and in high pressure, it leaves bismuth and goes to nickel. And whenever you have this ligand hole associated with bismuth, it gives rise to a checkerboard-like distortion pattern. So I have two different bismuth, one bismuth associated with two ligand hole and another bismuth associated with no ligand hole. And that gives rise to, back to your question with the bond length, the change of the bismuth oxygen bond length, one being long, another being short. That's all. So I just tried to show it in a cartoon picture. So you have basically a dancer, a dancing girl. Initially, she was dancing and holding hand with bismuth and applying pressure. This girl decides to leave the hand of the bismuth and instead starts dancing with nickel. That's all is happening. So the key player is actually oxygen. And others were basically not doing anything. They were just lending hand. And why does that happen? What causes this redistribution is nothing but by putting pressure, you are tuning this nickel to oxygen p charge transfer energy. And there is a big change, which in ambient pressure, this energy difference was 2.2 electron volt. In the high pressure, it becomes 1.5 electron volt. All you are doing is you are shifting the energy position of oxygen, nothing more. That's why initially oxygen was far from nickel and it was more happy to hold hand with bismuth. Now at the pressure, it becomes closer to nickel energetically and therefore holds hand with nickel.
So what's the kind of pressure that you have?
So this pressure is 3.5 gigapascal. So our proposed mechanism, which is shown in red and in black, was the mechanism proposed by the solid state chemist. So we feel all their things should be replaced by just the ligand hole story and nothing else. Bismuth and nickel are not doing anything. Bismuth likes to be in 3+, nickel likes to be in 2+, and it is just the ligand hole that is doing all the music. So indeed, our answer is too simplistic of view. Now, why the state 4 is not observed, why they didn't see the charge disproportionation at the nickel side? The only answer to it is we calculated the stiffness of the lattice, and at this high pressure phase, actually your stiffness of the lattice is way more than what it needs to allow to have this bond length being short and large, short and large. And so this is a picture. So as I said, when I introduced the peroxide with this A-side cation, so I said they are like the spectator. They don't do anything much. Active players are just the transition metal and oxygen P. So that's a passive role. We find that in this particular case, they have decided instead of being just like a referee and observer, they becomes a player and they makes an active role. In the specific case where your A-side cation has an extended s orbital that can easily hybridize with oxygen. And we did some of the model study in terms of now it's not bismuth nickel model, it's a 3-site model. We need to involve bismuth, nickel as well as oxygen because oxygen is our main player. So we have basically 4 parts of this Hamiltonian. You can just write it very easily. These are the on-site energies of bismuth, nickel, and oxygen. These are the hopping integrals, bismuth, oxygen, nickel, oxygen. In this case, nickel being a strongly correlated electron system, I have to put some U term, and that U term is shown here. In case of the bismuth, I do not have this such a strong thing, but I do have this restoring force because if this lattice is trying to contract and expand, there should be an elastic energy cost, and that is what is shown here. We note there is no negative U at the bismuth site because that was our goal. And then we basically solved this problem with the slave rotor approach. I don't know how many theoreticians are here. I only see Vikram. But anyway, so that is basically where you break down this in terms of some spin-on, which is a neutral thing, and a rotor field, which is a charged one. And what you achieve by that, by this separation of variables, you can have an exact diagonalization, which is basically a non-interacting problem of the spin-on, bismuth, and oxygen Hamiltonian. There is no correlation effect. All the correlation effect gets into the rotor field, and that was solved with the single-site mean field theory. And we use the oxygen on-site energy as the tuning parameters because by putting pressure, that's all you are doing. Well, what we find is the following, that the strong correlation is equally important as the bismuth oxygen hybridization. And this is the value of the correlations we are trying to put. If the U parameter on nickel site is small, these are all in electron volt, you have basically a transition between an undistorted metal to a distorted metal. By distorted metal, what I mean is big, small bismuth oxygen polyhedra, like a breathing distortion. If you make this U parameter large, this distorted phase indeed becomes an insulator. Because what you are going to do by this distortion is to make nickel exactly half filled, nickel 2+, which is D8, and you have a crystal field splitting, so nickel D splits into T2G and EG, and with the D8 configuration you can actually show then the EG will be half filled, and since there is no ligand hole, nothing, you now, like a normal mode transition, have to put a U to make that site insulating. And that's exactly what is happening as is shown with the spectral density plot. So we call them as A-site hybridization wave Mott insulator. To explain that insulating state, what I need is a strong correlation effect. So that's why it's a Mott insulator. But in addition, I need this hybridization between bismuth and oxygen to set up a hybridization wave, because I will have a big, small, big, small, some with 2 ligands, some with no ligand, 2 ligand, no ligand. That's an hybridization wave. And is it only the case for bismuth nickel oxide? No. Lead chromate, for which all the same Japanese group did a lot of experiment. Here it's the same thing. You do not have lead 3+, instead you have lead 2+ and lead 4+, that's what they believe. But in our picture, everything is lead 2+, and everything is chromium 3+, only the ligand hole, which was associated with lead, putting pressure, now goes close to chromium.
Can I ask a quick question here?
Yeah.
So, is there any signature that you can predict for the phonon modes in such cases when you have these transitions happening? And
indeed,
and that matches with experiment with that? Okay.
Yeah. Unfortunately, no physicists got involved into it, and the chemists, they don't do that kind of experiment. But
that's strange.
Yeah.
Okay.
And they didn't do any such experiment. Indeed, they didn't do. But in our calculation, we do see such a breathing mode. And
okay.
Yeah.
What wave numbers do you remember?
Sorry?
What kind of wave numbers for such a mode?
So your Brillouin just gets doubled. It's just a doubling.
Yeah, the Brillouin just gets doubled.
Not the Brillouin zone, unit cell gets
the unit cell. Okay.
The Brillouin zone gets halved.
Okay.
In this.
Okay.
So what we say that these will be seen whenever your A site has an extended S wave. Instead of bismuth and lead, they both have 6s. You take thallium, that has 5s. That should show exactly the same mechanism. So we know the Zanen-Swatsky-Allen-Fels diagram. We know the Mott insulator and the charge transfer insulator. We would like to actually introduce a third category, which is A-site hybridization wave insulator. And we indeed found some experiment done, not a great lot, and some spectroscopic measurement, which actually tells indium manganese O3, thallium manganese O3, they show exactly same kind of behavior. So how much time I have?
You have
Nothing.
30 minutes.
30 minutes. Oh, suddenly he's very generous. So then I can tell you the story 2. The story 2 is about the superconductivity in infinite layer Nickelates. So I partially fulfill your whatever you have written in terms of superconductivity. So that's basically, Pratap is here, who knows much better than me. So that's like year-wise how much the TC, superconducting TC has progressed. You do see a lot of excitations with the cuprids that happen. Then with the iron-based superconductor, and the new sensation to it, other than what is happening with the hydride, is the Nickelates. And that's the article from Mike Norman, entering the nickel age of superconductivity. And I will tell about whatever contribution we made in this area. But before that, I first have to tell the story of cuprids. And the story we had is that of an axial orbital. So this is a cuprate phase diagram. I think many of you know this phase diagram. So this is basically temperature, doping with a hole doping at the copper oxide plane. In the undoped situation, you have antiferromagnetic insulator. By doping, beyond certain doping, a superconductivity shows up and it has a dome-like shape with the maximum point of this dome is the TC at optimal doping. Now, we don't know, it's still debated what causes this superconductivity. Of course, one idea is the strong correlation that makes it superconductivity, but that may not be the complete story. So we'll not get into that debate. So what I just want to point out is how much variation of TC even within the same cuprate family you have. Lanthanum cuprate, where it was discovered, Benrose and Muller, again, two solid-state chemists. I love them. Maximum TC is 40 Kelvin. The same cuprate, you put some mercury, barium, etc., TC becomes 90 Kelvin. It's more than twofold. So where does this material dependence come from? There must be a reason that it comes from. We want to make TC higher and higher, so we should have an understanding. And clearly, this is nothing almost to do with the essential ingredient of the superconductivity, because if you believe copper oxygen is doing this superconductivity, then it is same for all of these compounds. Well and good. This is basically the Fermi surface. The Fermi surface is pretty simple because you have only one band that is crossing the Fermi surface, and this one band is a copper oxygen antibonding band. Very simple. You can write the tight binding Hamiltonian, do it. It's an undergraduate problem. But for lanthanum cuprate, you see the Fermi surface is more squarish compared to that of the mercury. Mercury is much more rounded compared to the lanthanum cuprate. And if you define some delta K between like how much it is bulging out, you can calculate something which we called as R parameter. This R parameter is 0.17 for lanthanum compound, and for mercury compound is 0.33. TC 90 Kelvin, TC 40 Kelvin. So clearly there is something between these two. And long back, 2001, we had this paper, and 20 years down the line, using the same idea, people actually published another paper in PRL, and we had to write a comment, and they gave some reply. So anyway, so what we found that it is just not the case for lanthanum and mercury. We did it at that time, almost all known hole doped high TC cuprate. We did this calculation. I will not get into the details of the calculation. We did all the calculation, very painful calculation. So this is more like a semi-empirical plot, because this R parameter is our calculation, and we did not calculate the TC. It's just measured TC at optimal doping. And if you just follow the black symbols, I will not explain the other symbol for the sake of time. You do find that there is a kind of correlation between this R parameter and TC, not for one or two compounds, but multiple set of compounds. Well and good. What is the structural element that determines this TC? There must be either chemistry or structure. Something has to happen. This is the high TC crystal structure, maybe well known to many of you. You have a copper oxygen layer, and you have lanthanum or mercury or barium. But most important for us is this oxygen, which is along the C direction, out of plane oxygen. That oxygen is known as apical oxygen. Point to be noted, this distance from copper oxygen plane to the apical oxygen is 2.4 angstrom for lanthanum cuprate and 2.8 angstrom for mercury. A big difference. And it is indeed true, this R parameter actually has a relationship between copper to apical oxygen distance, as is shown with the other, like bismuth, I think You are working with visco and thallium.
Tanusri, since these are all oxygen doped, that just could mean that the disorder effects are
No, these are all undoped.
These are undoped.
Our calculation of R parameter is just for the undoped compound.
But the superconductivity happens at finite dopage.
So what I'm saying that the undoped material already has the signature. If you optimally dope, what will be the TC trend?
You are saying that larger the R, the higher the apical oxygen is.
I'll come to that. Exactly, that is the thing.
So when they are far away, farther they are away, then the less effect they have by Coulomb's law.
Absolutely. 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 So then why it is like that? I showed you just a structural thing, right? That's this distance. So why is that? So the understanding is the following, that if you have an apical oxygen, which orbital of this apical oxygen will be effective? That's the oxygen PZ. Oxygen PZ is like this, a vertical object. X square minus y square is completely planar. So it cannot couple to it. But what it can couple to is copper 4s, which is empty and which is spherical in nature. So copper 4s being spherical in nature can couple to dx square minus y square, as well as can couple to oxygen PZ and or even further orbitals like lanthanum Ds. So this is exactly what is shown here, the copper 4s, which is empty, and that basically interacts with oxygen PZ and also with the lanthanum and maybe with the also copper 3z square, because that is also ml equal to 0. So all ml equal to 0 can connect to each other. And that gives rise to an effective hybridized object, a composite object, which is an axial orbital. And I will not get into the details. The energy of this axial orbital basically determines your range parameter. Higher is this energy, basically smaller is the value of this R parameter. So basically this distance is controlling the energy of this axial orbital, and this axial orbital is determining the range of this wave function in plane. So the more it's two-dimensional, more is this range parameter, means your wave function is more two-dimensional, higher is this copper to apical oxygen distance. So the essential material dependence is contained in a single parameter R. So that was the point of our whole exercise. And this parameter is controlled by the axial orbital, which is actually a hybrid between copper 4s, apical oxygen PZ, and also maybe copper 3z square, and also maybe lanthanum or mercury, but all has to couple in this direction.
Do you not see any contraction on the equatorial oxygen?
No, there is nothing. So everything is happening in this direction. So the wave function, I am not showing you the wave function. Either it is more contracted in plane, extended in this direction, which is for lanthanum, or not the bond length, but the wave function. Wave function is contracted and more extended in this direction, or the wave function becomes more extended in 2 dimension and less in this direction. And more two-dimensional it is, better it is for superconductivity. What will that imply for density of state? For density of state, it implies, actually, if you draw the density of state, which was evident from the Fermi surface plot, it will be much more symmetric for lanthanum. It will be much more, way more asymmetric for the mercury. Does it answer your question? I mean, by symmetric, I mean electron hole symmetry.
Yeah, that's fine. But in terms of numbers,
No. So we are not explaining anything in terms of the Van 't singularity. In fact, the Van 't singularity lies pretty low. So we are against the Van 't singularity picture. Okay, so very good. So here ends my copper story. So in the periodic table, nickel is just before copper. So copper 2 plus is D9. If we can make nickel 1 plus, that will be also D9. And then I will have another toy to play with. It's like a cupid. So that was the whole idea. Yeah. So, and there have been lots and lots of effort. So one idea was to put lanthanum aluminate and lanthanum Nicolette heterostructure. In fact, some of them made even a superlattice of it. And its electronic structure also have been very widely studied by Millis and also by a group from Castenheld, Ole Anderson. And the other where I also contributed a bit was from Martha Greenblatt, the solid state chemist. She tried in her solid state chemistry way. She made like, bilayer, trilayer cuprate. She made a multi-layer Nicolette and managed to get a combination of nickel 1 plus and nickel 2 plus, but not purely nickel 1 plus. She tried to dope it, couldn't find anything. So the matter ended there. Until and unless in 2019, there was a big hype from the group of Darrell Strom from Stanford, reported superconductivity in 20% strontium doped neodymium nickel O2 thin film put on Strontium Titan. Well, since then there have been, I think, many open questions and also a lot of debate. Are the Nicolette same as cuprate? The first striking difference, even at the undoped stage, they are different. Nicolette, undoped Nicolette, is a paramagnetic metal, bad metal, as opposed to cuprate, which are antiferromagnetic insulator. That means their magnetic exchange scale are very different. Now, if you do, this is again some of the oxygen cage X-ray absorption spectroscopy, and it shows that there is basically this oxygen cage peak is absent. So that means the cuprate, while it is in the charge transfer regime, because I mentioned of all importance of the oxygen, whereas for this Nicolette, it is in the Mott regime, oxygen having not much role. But there are Ritz measurement, which actually tells that the rare earth, which is the A cation, possibly has a role to play.
What is that measurement?
Sorry?
What kind of measurement was that?
That's a RIX, resonant inelastic X-ray scattering. So this is the structure of the Nicolette. You have all seen peroxide. So the only difference is this, in this case, the apical oxygen is missing, completely missing. So you have a nickel oxygen 2D sheet, and which are separated by this rare earth, which can be even a non-rare earth like lanthanum, either lanthanum or neodymium, this kind of thing. And this is basically the calculated electronic structure, which we calculated. We find that actually the band structure is pretty similar of that of the cuprate in terms of the nickel oxygen antibonding band, which crosses the Fermi level at 0 energy. That's all good. But there is another band, you can see that. And that band is a hybrid between empty rare earth 5D levels and the nickel 4s, like this copper 4s, as well as nickel 3Z square. It's a mixture of all of them. And that makes some electron pocket, both at the gamma point and at the A point. So if you see the Fermi surface of this compound, one shown for the neodymium, another shown for the lanthanum Nicolette, you have basically this whole light pocket, exactly like the cuprate, which is shown with the red. And in the blue, in the red, what is shown are these electron pockets, which are basically created by this band, which is a hybrid between your rare earth or lanthanum 5D states, which are generally empty, as well as mixture with the nickel S. Again, the S is a very important object. First of all, it's empty and it's spherical. So it can do a lot of things by coupling with others. And in contrast to neodymium, in case of lanthanum, you see this one just shrinks and almost disappears at the gamma point. If you make a description of the one-year function, you see the x square minus y square one-year function actually is more like the Cupids, except it is far more localized. If I have shown you the corresponding plot of the one-year function for the Cupid, it will be really, really spread out. It goes to fourth, fifth, sixth nearest neighbor. It connects to all different oxygen. Here, it's only to the nearest neighbor oxygen. But this object, which we call as our axial orbital for the Nicolette, you can see it's a pretty delocalized object. So this is your nickel 3z square and nickel s couples with many of these 5d of this lanthanum or neodymium, and that makes such a connected wave function. And the shape of this wave function of this axial orbital is quite different between neodymium and lanthanum. That's our axial orbital. Okay, so with that, we did two-band modeling. So this two-band, one is the x square minus y square nickel, and another one is this axial orbital, which is a hybrid of lots of different things. And then the interaction, so the calculated electron phonon coupling is actually small. So we didn't therefore consider any phonon mechanism. Instead of that, we had this correlated mechanism. So we had this interaction term, which is a U term, which is U between x square minus y square and x square minus y square, axial and axial. But we had a V term, which is connecting between the x square minus y square and the axial. That's an interorbital interaction term. And within the RPA, by summing up the bubble and ladder, we could write the pairing potential, and then the superconductivity problem was solved through this self-consistent equation, where delta is nothing but this superconducting wave function, and that's basically the strength of the pairing. And since it has a k dependence, from there you can also talk about the symmetry of your superconductivity. So what we find in neodymium case, it is basically a two-channel superconductor where there is x square minus y square like a cupid, but there is an additional channel which is contributed by this axial orbital, which is gapless. And actually there are STM experiment, which agrees with our viewpoint with a two-gap superconductivity, one being x square minus y square type, another being gapless. And for lanthanum Nicolette, actually in this other channel, there is absolutely nothing, because this axial orbital I showed you, that has a very little electron pocket that's almost disappearing. So this is a superconducting coupling strength plotted as a function of this interorbital interaction V, and that has a very strong effect. By making it little larger, you actually have the lambda shooting up. So again, I'm back to this story. I like this story. In case of the Cupid, the axial orbital was important, but it had a kind of an indirect load. It was not actively participating. It was influencing the R parameter. It has an important influence, but still it has a passive role. In case of the Nicolette, it's an active role. It actively participates in superconductivity by opening up an additional channel. So is neodymium Nicolette the only candidate? The answer is no. Again, there was paper from the same Stanford group where they found superconductivity in praseodymium and with almost the same transition temperature as neodymium. Now, neodymium 3 plus has 4F3, praseodymium 3 plus is 4F2. So that means I'm changing the valence 4F electron, but apparently that is not doing much in the superconductivity. So the 4F possibly doesn't have much role in it. If it is so, in what way they are important? So we did the calculation for neodymium as well as for praseodymium and lanthanum I showed you already. We find both for neodymium and praseodymium, this electron pocket, which was given by the second orbital, namely the axial orbital, they are exactly the same. So that means it's the empty 5d that matters, not really the 4f. But 4f has a role because in case of lanthanum, there is no f electron. If I put some f electron, that actually pulls down the energy position of this empty 5d level, and therefore its interaction with the nickel becomes different. That's the role of the 4f. It's just a Madelung energy, if you like.
Then that can be tested with other lines.
Very difficult to make this sample, and very few in the world has observed superconductivity, very few. So I was discussing with Rajdeep, he could not be here, so I discussed the whole thing with him. It's actually there are a lot of, first of all, it is observed only in thin film. It is not observed in single crystal. No one has tried it in the single crystal of neodymium Nicolette, but lanthanum Nicolette infinite layer, people have tried a lot. They could not see it. But in the thin film, they could see it.
What about like gadolinium?
Gadolinium, I don't think there is any experiment, but even if you do gadolinium, my bet will be, it don't change much. So I show you here what exactly is the effect. So praseodymium and neodymium, this axial orbital density or state is shown with the black, and this is basically nickel x square minus y square density or state, two-band model. So projected to these two orbital, one is the x square minus y square, and another is the axial orbital. 0 is set at the Fermi level. So you see in case of the neodymium and praseodymium, the occupancy, yes, I will finish very soon. So the occupancy, because you have one electron really, and here if you have 88% of it goes to the x square minus y square channel, but 12% goes to the axial orbital channel, both for praseodymium and neodymium. For the lanthanum, this drops to only 7%. So that's a big thing. And with that, we actually computed the doping dependence. We could not really go to the low doping because there our theory will fail. So that's basically our artist construction. So you find for neodymium and praseodymium, we expect the TC to be similar, while for lanthanum, it will be strongly suppressed. When we published our paper, there were no experiment on lanthanum because they could not make the lanthanum superconducting. But after our paper came from same Harold Wang group, the phase diagram, but they have, I don't know, maybe they got motivated by us, praseodymium, neodymium, and lanthanum. Exactly the TC of praseodymium and neodymium are very similar, while for lanthanum, it is suppressed by about a factor of 2, which was also our prediction. So, thank you.
This is very nice. Thank you, Tanusri. So the talk is open for more questions. Yes, Father.
So in this second part of this Nicolette superconductivity, one thing is all this superconductivity observed when these thin films are grown of Strontium Titan substrate. So I'm wondering what role the substrate is playing here, because other than in a single crystal or without.
So one debate is, first of all, this is not really tried with a single crystal of neodymium Nicolette or praseodymium Nicolette, but lanthanum Nicolette has been tried indeed and for a long time, and people could not make it. Why they could not make it? First of all, the strain doesn't have much role, in the sense if you're thinking of strain, we actually did calculation by straining the thing. I didn't.
I'm more wondering in terms of doping coming from.
No. There is no intermixing. They showed everything very clearly. Since you asked this question, so how do you do this infinite layer? This reaction is known as a topotactic reaction. Topotactic reaction means the apical oxygen has to be etched out. And the way to etch out is to use the reagents like calcium, H2, NaH. So the one proposal, there is a paper in Nature, March this year, 2023, and we are trying to do some of the calculations where they are saying actually there are trace amount of hydrogen that are remaining in the sample, and these hydrogen goes and sits in the apical position. So that is their theory, although I have some reservation on it. But other than Harold Wang, there are few other groups, they have also reproduced it, not everyone, but all in the form of the thin film. Now you can ask why this thin film was necessary. I don't know. I am not really an experimentalist. It's wrong to ask me that question. It's for the experimentalist to answer. But we are actually debating on what is the role of trace amount of hydrogen if it is remaining in their sample. Especially if there is a hydrogen in this apical oxygen position, what will be the composition of this axial orbital? Will we still see such kind of two-gap superconductivity? Apparently, this STM says very confidently. And other than STM, there is also Hall data, which also claims very clearly there is both electron and hole-like carriers.
Is it proton or hydrogen?
Proton.
It's proton.
No, sorry, not proton, H minus. H minus, not protonated, H minus. And of course, they could not say whether it's H minus. So this H minus is a result of a calculation. It is not their thing. Hydrogen is very tricky thing. You can't see, you can't measure, you don't know how much hydrogen is there and what is the charge state of it. So the calculation says it is actually not protonated hydrogen, it's H minus.
So I had a quick question about the U parameter that you use. So is that you put it after the calculation, or is it you know it a priori?
No. We don't know it a priori. So I think the U parameter you are saying was in the context of the model calculation we did for this bismuth nickel O3, right? That's where you are saying.
That's the one, yeah.
So this is just to show the effect of U. U I'm treating as a parameter. And what I'm showing you, if the U is low, even if I have a distorted lattice, I still don't have a metal. So your correlation is important. And to make it an insulator, I need to go beyond certain value of U. That's all I'm showing.
Okay.
And possibly for nickel, U is not really 2.5 eV, nickel oxide. There are a lot of spectroscopic examples of what will be the U value of nickel, and it is probably more like 6.5 or even maybe even a little larger. But what I showed you, to make it an insulator, I need to bring the U larger than certain value. Otherwise, I don't get it an insulator. That's why we called it as a Mott insulator, which has a correlation effect together with this A-side hybridization. Not just A-side hybridization insulator, because correlation also has a big role to play.
And I was just curious, this U parameter, it usually, is it K dependent or it's not?
No, this is a static U, has no K dependence, no omega dependence, nothing. It's an on-site Hubbard U.
Are there ever situations where you need the K dependence? Or?
Of course. There are plenty of situations. I think Carlo is here. Like there are lots of things with the spectroscopy of the simple nickel oxide with many subbands, which you cannot match until and unless you have the K dependence. So definitely. But in this case, we are not so much concerned about at which precise value thing will happen. All we are trying to show that correlation is indeed important, because if I make the correlation effect small, I get it as a metal. The approach is a little different. We are not so much reproducing the exact number. Instead of that, we want to understand the basic mechanism and the trend.
Thank you.
If that answers your question.
Yeah, so very interesting. Here's something from somebody who is completely out of the field. But I saw that the wave functions that you're talking about are highly anisotropic, their extent. And I heard a lot about recently, maybe a year or so ago, about this single directional superconductors. Can these materials achieve that? Or
sorry,
the single directional superconductivity. almost like a PN junction kind of thing.
No, these are not like that.
No, these are not like that, but I'm
These
saying
are
that these
like that.
materials, would it be?
First of all, I did not follow your question correctly, and the answer I'm giving you, I don't know whether I'm giving you correctly because I didn't quite get your question. So all the anisotropy is because if you look at this cuprate superconductor crystal structure, even structure-wise, they are highly anisotropic. If you measure their resistivity in plane and out of plane, they are very different. So they are very anisotropic to start with. Now, if you are asking about the superconducting order parameter, is it isotropic like a S wave? It is not. It is more like dx square minus y square. But we didn't really, in the cuprate, we didn't look at it. In the Nicolette, indeed, we looked at it. And it is like x square minus y square. So your superconducting gap will close in certain nodal direction, but will survive in certain direction. If that answers.
All right, yeah, I'll talk to you later.
Yeah. So I have a simple-minded question. Like you have shown a scale of this oxygen transfer energy, like oxygen energy. Yeah. So can you go back?
Yeah. That was at my very first slide. Is that what you were asking?
Yeah, no, that previous one. No, not this one.
Yeah, it's much before.
No.
Here.
No, the later one. The later one.
With the pressure tuning this?
Yeah. Ambient
Okay.
pressure and high.
Yeah. Sorry.
Yeah,
I think you were
this one,
talking about this.
So
right?
here you have, in this case, in the ambient case, where the thing is comparatively, the energy scale is comparatively greater than the high pressure thing, but still that is the energy gap is greater than the Bi2 and oxygen energy.
Very correct.
But still
Absolutely. Thank you for asking it. Because hybridization, which we call hybridization, that's T squared over this delta. Okay. So for nickel to oxygen, this T is small because wave functions are much more localized. That's why I am mentioning extended wave function. This 6s is much more extended. Think about your hydrogen atom problem. 6s is much more extended than your 3D. So therefore, this T, which is basically overlap of the oxygen P wave function with this other wave function, is much larger. Absolutely, you are correct. But even then, this hybridization will be larger with bismuth simply because even the delta is large, small, but the T is also large, and it's T square over delta.
Yeah, I get it.
Okay.
Okay, sorry. Anyway, I couldn't hear the first one.
I had all this spectroscopy. You were not there.
Unfortunately, I caught up in a meeting. Anyway, it went for a long time. And the last part only I saw. So that calculation is a slab calculation, or the last that Fermi surfaces that you were showing. This I think LaNiO2.
Yeah.
So,
No, they are not slab calculations.
no, I just wanted to know. I mean, is it a?
No, they are bulk. I mean, thin film is very very thick.
So these calculations, I mean, you didn't consider this thin film geometry or something.
It's not needed.
I see.
Because the thickness of the film is
pretty
in
large.
macroscopic scale.
I see.
So you don't need to do this.
Okay, so two things I wanted to know. One is that the gap that you are getting, is it dependent on you, or how does it depend?
Yes. I rushed through it. You can see that this lambda, which is the strength of the superconductivity, is actually here I show the U dependence. And U, it is not very strongly dependent on U, but it is strongly dependent on V.
I see. Okay.
So you need a certain value of U, otherwise it will not show up. But then the variation as a function of this U, after the U crosses certain value, is not so much.
It's not so much. Okay.
On the other end, with a V, it has a tremendous effect.
Okay.
Tremendous.
Okay. The other thing is that from these plots, it looks like that these are not effectively two-dimensional systems.
No.
So these
not
are a lot of.
That's why we are saying it's not like cuprate. It's not at all a two-dimensional like system.
Okay. So let's thank Tanusri once again for a very nice question answer session as well and the talk. And we will all move to the outside the West Canteen area for a little bit of snacks. So thank you.